I need join now. Oh, I'm alone here. I'm not sure. Someone connects to Teams. Okay, anyway, stream is alive.
Yeah, he said he's on the stream.
Good. I see 0 viewers, but not important. Statistics sometimes look very strange. Yeah, 1 view. Okay. Let's go. Let's try to do something. What I'm planning for today is a section of signal theory. It's called system with return. Idea. What if we have, let's say, some linear system, what can be described as, for example, as linear transfer factor. It has something on the input and it has something on the output. The idea is what happens if we take output and add it to the input. Let's say this will be bad. Let's try to understand what happens if we supply output signal to the system's input. It might be called feedback or simple return. At first, we will analyze such system. Is first I need some example of linear system. Previously, we saw something like this. For example, two resistors. Let's say Ux and output some Uy. We can write what output voltage is input voltage multiplied by and divided R1 plus R2. This one is linear system, isn't it? With the scale factor being R2 or transfer factor. But can we get in all such systems transfer is less or equal to 1? Can we get amplifying system? To analyze feedback, we need system with this transfer, let's say factor or scale more than 1.
Why?
because we need to compensate energy losses in feedback. How can we do it? How can we get? I have one very old idea. I'll need this guy. Where is my old idea? We need an example. Example, 2 minutes. I got a box. And inside box is a small piece of woodworking.
That's an eyeball, right, Professor?
Yeah, it's so-called triode. 3 electrode.
3 there.
1. First I need to get it visible. 1 second, I'll come closer. I think it's okay. So I have a evacuated sphere with no air. Where is my power supply? And wires. Oh! Connect. Wires. Yes. The element number 1 is a heated cathode. Now it's been powered from supplementary power source. It's not important. We can see it's red hot. It's heated. I also have a grid or mesh. I will try to show it. Heat is above cathode. this one is green, and I have, let's say, yellow anode as this white metallic disc. If we have some, let's say this one is earthing, anode will have positive voltage. If we have something hot, we may remember what thermoelectronic emission. So one electron can leave the hot surface. And what will happen next? We have a positive potential here. So we will have a dragging force dragging this electron to the anode. But we have a mesh on its way. If it will have negative charge, is negative, it will deflect our electrons back to cathode. If it will have positive charge, it will drag electrons up, so let's say boostify them. They will have acceleration on their way. What we need to do? We need to set a simple experiment. We need a switch.
Professor, isn't it the other way around?
Okay?
Minus, if it's less than 0, it should be attracted.
If it's less than 0, they will push them back. Electrons have negative charge.
But they are attracted to the plus.
Yes, they are attracted to the plus,
Yes. So it
but grid is on the way. Electron flies. If there were no grid, example, here. Two electrodes divided. This one has only two electrodes, hot cathode and cold anode. If we have plus here and minus here, electrons fly up.
Yes.
If we have minus here and plus here,
It goes right down.
they can't leave cathode. And they remain as a kind of cloud near cathode. They can't reach anode because there is no dragging force. Here we have free electrode system. Anode always attracts electrons,
Yes.
but they need to pass the control grid. If it has negative charge, it will push electrons back.
Yes.
If positive, it will accelerate them on the way on the road to anode. But we need to see. 1 second. Why I wasted so nice board on all this experiment? So I will switch milliampere meter into anode circuit, and I will use what I will use. This will be. I will use potential to change the grid potential. I will use, I need to measure them. Come to me. This one will measure anode current. Let's place it. Let's say here. You see a lot of wires here. Wires. More wires for the cut of wires. wires for the god of wires. I need to supply positive voltage. So let one here. This will be current, and from there this way, and this way, and now I need, yeah, this will be ground wire. Here, and I also need this one. Oh, I have current, and I'll need voltage. I need voltage. Voltage, 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 voltage. I need voltage. This one will be voltage, and I need to get it's not a very good idea, but the idea, take this one. This one will be ground, and there is one. Okay, I can take this red wire. Get my now this. And yes, now they have 2 meters. This one measures grid voltage, and bottom one, lower one measures another current. And let's see what will happen.
So the below one is voltage?
This one is voltage, upper one, and lower one is current. Now what we got, 72 volts. Current is 0. Let's go to plus. Minus 40, minus 18, minus 6. There we are. Minus 1.3. 0.8. You can see 48 microamperes. 2 volts. 67 microamperes. 6 volts. 170 microamperes. 7 volt plus. 136. 12 volt plus 174, 18, 188, and stable. No more growth. I can go backward. Current falls, and no current. Current appear. We can see growth, and it is saturation. I can draw a curve. I can draw a small curve. Of course, it's approximation. Anode current. What we see? Nothing, growing, and then saturation. Something like this. So this valve can be seen as a resistance. It's Ri, internal resistance. Something like this. Okay, example, resistance, but controlled by ego. We see. Okay. What now? And now I'll try simple schematics. My lamp. I will put here will be plus, resistance, capacitance, and output. At input, this will change a gap. And here will be a 6. And here we will see a cigarette. Can we? What will we need? Scope. We need to see. B. Come on. very smart to put a power supply on a scope wire. Okay, scope will go. Scope here. I want this will be source of input signal.
Professor, why do we need input signal? We are taking the output signal, right, from the three-phase.
Yeah, very interesting how this thing works as a stage. We need to understand what happens when we put something on input, what will happen on output, to understand its behavior. Now we see this chart.
Yeah.
But what?
This is for DC.
This is for DC,
Yes.
and now
We'll do AC.
we do a signal. Possible, we will be able to get signal here. So I need to this one. This one is sorry. So like this. This one goes here. I need here, and how will I get my signal there? Do I have wires? Okay, this one will bring signal to the grid, and from the grid I need switch it off. Which is so noisy. Ground connected to the ground. Where is my wire? This one is not good. Cool. Easily. Yeah. I have signal. Maybe I need to move camera.
That's the input signal also.
This one is input. The yellow one is input signal.
Sine wave.
Yeah, it's a poor sine at 8 kilohertz. It's so important. Maybe I'll use a lower frequency. It's not important anyway. Something like this. And I need output. Here is the output line. Now I have grid voltage minus 64 volts. Minus 3 volts. Input, output. Maybe I need 1 second. I have channel 2 active. I will co-measure. Not frequency, not period, not peak to peak. Values. Yeah. Okay. They are not in one scale. Yellow one has 1 volt per centimeter and blue one 5 volts per centimeter. What's going on now? We have an offset minus 3.8 volts. We are here. No, we are here. I'm applying yellow voltage like this. What? What? Yellow voltage. Like this. It's 1 volt ineffective. I have to, and see what's going on. When voltage is negative, see, it's being cut off. Because on the characteristic, this part is not valve is closed. When voltage is positive, you see the current flows. But output is negative, because I have a divider here. This schematic is equivalent to the fixed and voltage controlled resistor. When I have current, this resistance diminishes and voltage at the output goes down. So at this point we see, what do we see? Cut off, half sine. Cut off, half sine. It's not good. System is linear. No. Let's try to change set point. Oops. And what will you say about this?
He turns it upside down.
Yeah,
flip side.
We have 1 volt at the input,
Yeah.
7 volts at the output, but negative.
Negative, yes.
We have amplification. Now the working point is somewhere here.
Input.
This again is Sx as time. Output will be what we will see.
Amplification, but it will be negative.
Amplification, but with negative sign. We have system with a factor approximately -7. It's linear, it amplifies, but inverts.
Yes.
It's normal virtual or amplification system on the single stage do invert. So we got linear system. Good. And what if I shift the work, let's say, operation point further to positive? See distortions and
Professor, you are shifting the input.
I have shifting the offset voltage
Okay.
to this point.
Oh yeah, okay.
I have shifted offset voltage to somewhere here,
Yeah.
and we see distortions and amplification.
Smaller. So it's almost like resonance? Something like that? It's like,
No,
it works at a specific frequency.
offset.
So
It isn't frequency dependent on the first approach. It is frequency dependent because we have capacitance, grid cathode and grid anode. And the both we have capacitance anode cathode.
Yes, but the offset voltage is
Yeah, offset voltage sets a working point. No, I don't think it's similar to resonance.
So it's like below a certain voltage
It's-
and above a certain.
Yeah, at this point, nothing, no output at all.
Yes.
At this point, distorted. It's clip. It's going to clip off. So, at this point, we have linear amplification, and forge we have disturbance.
Distortion again.
And if I go
Higher?
high, no amplification at all, because we are in this horizontal area of characteristics. Yeah, here it is. Now we have linear system, 2.2 volts offset, average current 53 milliamps. Nice linear system. So this technology is obsoleted. Now it's used only on high-end acoustics. It's very inefficient as consuming energy, but sound is beautiful. So client pays.
So in the modern world, what do they use instead of this?
Only very extreme system, high frequency system. And now virtual only application area, high quality acoustics. It's an old technology, but it's simple, it's good for us. We need something simple. And linear. We need something simple and linear. So, now we can try our object. Our object is system with return. Now we have linear stage amplifying.
Yes.
What happens when we use part of the output as give it back or send it back to the input? Okay, and I can switch it off.
Professor, is there some kind of equation or something to find?
Yeah. One second. Definitely, there will be one. There will be a lot of. Go to bed. I'll use this one. It has schematics assembled, and it's better. It's better because it's high amplification rate. Now, I need a theory here. Some theory. I'm not trusting myself. This is my board. Oh, yeah. Yes. I'll switch screens. So, let's say we have an amplifier. Let's say input is and output is on. And we have a feedback network, what can be characterized as with a transfer function beta. With the output that input is just on. Let's start from example from the harmonic input.
Professor, what can we call this topic?
It's our system with return.
System with return.
Previously we saw this element.
Yeah.
Now let's see what will happen when we add a feedback. We saw example of linear amplifier. try to understand what will happen when we add a feedback network. This direct network has an amplification factor of K. Now question, what will be amplification factor divided by E for the closed loop system? What will be transferred for the closed loop system? Is under question. At the output of feedback, we will have its transfer function multiplied by output voltage. It's clear. But output voltage itself is an amplification result of sum of two elements. Can be written as omega multiplied by A plus beta U. If we solve this equation to get the output voltage, so if we solve this to get output voltage, we will have voltage being direct amplification 1 minus direct amplification feedback. What we will get? Multiplied by E. So, transfer for the closed loop system is transfer for the open loop system. 1 cup beta here it is synthetic characteristic. In the terms of Laplace transform, to get it universal, if P is omega complex frequency, closer to transfer will be of our amplifier transfer 1 minus amplifier transfer return transfer.
Versus C is capacitance?
C here is constant.
Constant.
Laplace transform. When we from
And what was the other neuron after the
G omega,
K0P? Okay, that's the new
yeah, K0 resulting transfer
in Laplace transform.
in Laplacian space.
How does that help us? Laplace transform.
Laplace, yes. When we from Fourier transform, where we have frequency, switch to the complex form, C plus omega complex frequency.
And then we need to bring it back also.
Yeah, it's problem but solvable. It isn't very easy,
But we have to do it.
we can do it. So this one is not needed. Now the core question. We can create a synthetic characteristic of the system with the feedback. Feedback may be positive and may be negative. We can switch sign. Now the core question is stability. There are stable system and unstable system. If I have ball in a grave, the system is stable. You can do what you want, but ball, after any let's say disturbance, returns to its stable position. Ball on a hill is not stable, it will fall. Limited stability. Now question, what about our system? System with return. See, if we can play with return characteristic, we can create maybe stable, more stable, or maybe less stable system. How to understand it? Let's say stabilizer. We want to keep voltage. Load changes, and we need to keep voltage. If load increases, voltage decreases, we need to add more power.
Yeah.
What's the sign of feedback? It's a system with feedback.
Yes, yes.
What will be sign? Positive.
Positive, yes.
Maybe such system may become unstable. What? How? Where to work? In general, we can start from the, let's say, global approach.
But Professor, if the output signal is negative, then the feedback is also negative.
We will see now.
It depends on the transfer function.
Yeah, it depends on the transfer function of direct, let's say, stage and return. Wait 1 second. Let's say we have system what can be described with the uniform differential equation. Something like A0 and derivative of the x. X is some signal. A1 and minus 1x t minus 1, it's my n minus 1 derivative, plus, I'm lazy, a plus x equals to 0. Let's say we have a system that can be described with such differential equation. Here x as a function of time, what is called process variable in the theory of control. It may be voltage as current, it may be current as a function. It's actually some signal. And we have set of coefficients or factors describing the system. Such kind of equation, well known, and solution well known. Solution equals from I AI constants F power by I T, where A are constants and phi are roots of characteristic equation A0 t power n plus A1 t power n minus 1 plus an 1p plus an equals to 0. Characteristic, so-called characteristic equation. Solve this equation, get roots, and these roots will describe your process. We solve it with lambdas on oscillator process, where we have two roots. For more complex system, there may be many roots. Anyway, if system can be described with a differential equation, solution will look like sum of border condition constants and roots of characteristic equation. Yes, I'm here. So, system may be stable or maybe not stable. If system is stable, after any, let's say, any disturbance, it returns to its stable position. It will shake and settle at all. And for such system, real parts of all should be less than 0.
For it to be stable.
Yeah, the system, this means what energy will dissipate. If we have a heat, system receives some energy from outside. If all roots have negative real part, energy will dissipate, go to heat or something like this, and system will go to at last to a stable condition. If any one root has a positive real part, this means what at this frequency. At this frequency, energy balance will be positive and system will go up to destruction. Possible. It will not be stable.
So only at that frequency, or
each root, they can be real root without image path. If roots are real, process go like exponent to the 0. If we have complex root, they usually are conjugated, and they describe oscillation their imaginary part describes oscillation frequency, and the real part process it goes down or goes up. Why I have a linear element on my table? Wait a second. And it's one important moment. Characteristic equation is nothing that's the divider of the common transfer function. Let's say we have system under, let's say, output is voltage. There is a feedback somewhere inside. We can write for such system what kind of equation? A0 the n plus A1 n minus 1 dt n minus 1 plus a n u t equals by e. That's what we will have. If we apply Laplacian transform to the t, what we will get? Its image as a function of complex frequency. Yes? And this one will transfer into, will transform into A0 image plus A1 Pn minus 1 plus A1 P plus an image of the voltage equals to the image of the input. So, collect all voltage and you will have uno multiplied by A0 Pn plus A1 Pn minus 1 plus An equals to E to the image of E. Meaning what transfer function divided equals to 1 divided by A0 nth root plus A1 plus AN. Here it is. Transfer function has divider has characteristic equation as its divisor. Zeros of characteristic equation means own frequency of system, frequency at which system will oscillate or go exponential down. Each such frequency equals to the point where transfer function becomes infinite. Because you have division by zero here. Each pole or place where point frequency at which transfer function goes infinite means own frequency and potential point of instability.
Then the characteristic equation will be zero.
Yeah, the points were zero. It may go down, oscillate, but decaying oscillation, or it may go up. So what we can conclude, system is stable. System is stable if there are no poles. We can divide. This one is omega. It's a plane of P. If we have all poles in this area, system stable. Not stable. Here's the border. If you have any pole, meaning root with positive real part, on the right side, system will not be stable. Or at the left, system stable. I have an example.
Professor?
Yeah.
You can finish in like 10 minutes?
Let's try, but I'm not sure. Okay, we have time.
Because I need to run for another lecture at 2.
Okay, I'll draw schematics, and I think experiment will be next time, because I'll need to assemble network. But schematics, let's say we have my valve, cathode asset, coil capacitor, plus 250, and here resonant. Here will be resonance load. Resonant amplifier. This resistor is added to show losses, coil and capacitor losses. And here I will have this one from net. One interesting network. I will use coil link it to the main contour with the control of metal inductance. With this induction, inductance.
Is there a switch there? No switch, right?
No, not a switch. I have connection here, but I want to use this pair of coils. Where am I? Here. I'll use this pair of coils. The bigger one will be this one. It will work as a resonance circuit. I'll have capacitor here. It will be resonance circuit. And this one, smaller, will be used as a feedback. The idea, I can move them freely. With direction, I change, let's say, amount of feedback. But also, I can turn coil, changing the sign.
Yeah, plus minus.
Plus, minus. So I can freely control feedback with the simple meaning, changing position of small coil. Nice coil on the aux stand.
So that 250 is the voltage or something?
Yeah, it's positive voltage. It's just an anode voltage. It's plus 250. This 250 soon will resonance circuit.
So that is how you are going to give the feedback, right?
Yes, I will organize feedback using
A resonance circuit.
metal flux, common flux between resonance circuit, here will be capacitor. This part will be resonance circuit, and feedback will be controlled via common flux of yellow one and this small, nice small coil. Looks ancient, but it's a reproduction. The one with the black faces is original from 20s, but these are reproductions. I found one small business in Italy producing these coils. Simple coils without frames, without bases, and this was a plus. I don't know, rejected or failed commission, but they are okay for me.
They work, yeah. There are windings inside.
No, it is a binding.
Ah, okay.
It's like a kind of space structure.
Yeah. But doesn't it have to be a circular winding? It doesn't matter.
It is circle. The idea of such winding is to minimize interturn capacitance.
It goes like this.
Yeah, it's called B. What B's are making? These hexagon structures.
Triangles.
No. B's form the nest in form of interconnected hexagons. So it's a B nest.
B nest.
It's
Yes, B's, yes.
Such structures were popular till some 50s. There's a problem. Intervening capacitance limits frequency because appears resonance part of the coil. If we make a coil in kind of layers, between layers also occurs capacitance. So within one layer and interlayer capacitance appears its own resonance frequency, and coil not working as one. It splits into separate resonance contours. So to prevent it, one of the techniques was to use such kind of winding. It takes a lot of space, but capacitance is much smaller. Between layer capacitance are smaller compared to such coils. Another solution. This one is also has a similar cellular structure. This one is original.
Is original.
This one is from the 20s. It's from the receiver, French. Nice cool. This one is from France. Do I have something? There is some turning. I don't know. There are somewhere. What kind of coil I have here? No, it's just in section. It's sectionized. It's not so beautiful. No, it's all glued together. This one is made so-called universal system. Not sections are like discs, and inside wire goes not just turning, but always like wave to increase. What to increase? It's to increase quality. It means decrease interwinding capacitance. Works. Okay.
And Professor, capacitance is because of that gap between the wires, right?
Yeah, it's a higher gap, the lower capacity.
Yeah.
If wires
Are like this close to each other, then yeah, the voltage between.
like here, we have quite significant capacitance, wire to wire.
Yeah.
And it's mean partial resonances, small resonance contours at a high frequencies.
And Professor, every gap will have its own resonance, or
There will be very complex system, each turn against turn. So turn with its capacity creates one contour, and one layer of the coil to another layer, another. It will be it will make a very complex picture. Quite disturbing. Okay, as I understand, we are limited in time. Okay, what we can do, we will continue next time with the experiment.
Professor, maybe we can start early next time. Yeah. I'm saying since every other week we have only one lecture, we can start at 12 or 11. Or, yeah, we usually
I'll
start at
be here at 10.
Next week is 10:15, but I'm saying the week after we can start a little early because we need to finish early. So
We can try.
I think 12 o'clock is more.
I'm free from 10.
So I can inform the others. So we will start at 12, so we can finish half an hour early. Then we will have the same amount of time.
Okay, we can. I don't know why such complex shadow was created.
Yeah, it was. I think because it was created because we were supposed to have practicals every other week. So every other week we have 2 lectures. Today we have 1.
Strange. I offered all from 10.
Yeah. But we don't have anything before. We only have law subjects. So.
Strange.
Yeah.
No problem. We can do it. Okay, we need to stop for today. So next time I'll show effects of feedback. Yes, and we can do a little research into resonance transformer also. You can find it fun. 2 viewers. Okay, it's enough for today. Let's see you next time. I need to show